this video, I will go over how to evaluate some of the terms on the control surface which does not have a uniform distribution in their variables. I'll use this example for the surface mass flux, but the same idea can be applied to the other conservation laws such as the momentum conservation and energy conservation. So before I talk about how to integrate these variables, let me just draw the control volume surfaces. So here is my control volume CV. Its surface is termed control surface. I'll be using this acronym. Then on this control surface, we want to evaluate this surface flux term. On the control surface, I want to evaluate this rho times fluid velocity dotted with the outward unit normal vector, which I'll talk about. So then on this control surface, and because this is a three-dimensional object, so we need to think about this unit outward normal vector. So N, so this unit outward normal vector characterizes the control volume, more precisely control surface. On certain areas of the control volume or control surface, we have fluid particles going into the control surface. Okay, then I'm going to call this such area as CS, N. So I'll characterize this later. And whereas on the other regions of the control surface, fluid particles are leaving the control surface. CS out. So this mass flux is shown here. So because on the control surface, you either gain or lose fluid particles. So this can be expressed in terms of this superposition of this integral, because the integral is a linear operator. You can use the superposition. So how much mass you're gaining and how much mass you're losing on the control surface. In case that the fluid particles stay on the control surface, you can either consider as whether you are getting fluid particles or getting fluid or losing fluid particles, because in that case, this U dot N term is 0. So this mass flux will be 0. So it's not really a concern. So it's going to be either control surface integration of the control surface. Then you're going to split this integral to these two parts. Then we have this U dot N. So the way we do the integration, in case that the variables is not uniform, you need to think about this infinitesimally small area element. Here I'm going to call this area as dA, and I'm going to draw it here. So we have this infinitesimally small area. So that's why we have a D operator in front of A. And again, we want to use this unit outward normal vector N hat. And this is a unit outward normal vector. So this characterizes this infinitesimally small element. Unit in a sense that its magnitude of U hat is square root of the inner product with itself. That's going to be 1, and this is a unit. Outward, meaning that this vector is pointing outward. It's basically pointing the surrounding of the control volume. And normal in the sense that this has a 90-degree angle with the control surface. So in this particular example of the control volume, so say if you have a fluid velocity on this infinitesimally small area, so let's say you have a fluid velocity like this, and as you can see in the mass flux, the only term that matters is not u itself, it's actually this u dot n, the projection of the fluid velocity along the normal direction of the surface. Because only this normal component, I'm going to call it as un, this is a normal component of fluid velocity projected along the normal direction of the control surface, because only this normal component contributes to the change in the surface mass flow rate. So if this angle between this u and n, so if angle between vector u and n and head is less than 90 degrees. So that is the case you see here on the screen. So then u and n, they are both pointing the surroundings of the control volume. Then this u dot n, by definition, is in the product magnitude of u, magnitude of n, which is 1, and cosine theta. So because angle is less than 90 degrees, my cosine is positive. Therefore, this should be positive. Okay. So then this normal component is positive. So for the same, following the same reasoning, if the angle between the u velocity vector u and n normal vector is greater than 90 degrees, then fluid particles are going in. So this is going to be the blue arrow here for u will be pointing inward. Then this u dot n is negative. So if the angle is greater than 90 degrees, so then this u dot n, which is the magnitude of u, magnitude of n, which is 1, cosine theta, at theta greater than 90 degrees, its sign is always negative. So mass influx and mass outflux. So the sign of the normal velocity component, that is important. So with all these basics in mind, let's move forward to evaluate this integral on the control surface. So let me do this quick example. So we have this horizontal pipe. So we have this horizontal pipe, and it's a circular pipe, meaning that its cross-sectional area is a circle. So then let's try to apply this. Let's try to evaluate this surface integral, surface mass flow rate. So the first thing you want to do is to set up a control volume. So this, I'm going to use this particular control volume so that I can do this integration. So it is probably similar to what I do in the class. So this is my control volume, and therefore its surface is a control surface. Then we first identify the outward normal vector. So this is the, say, if I call this as a location 1, surface 1, and this is surface 2, so circular area. So I have outward normal vector n1 head. I have outward normal vector n2 head. I don't care this in the side surface, I mean this region, because the fluid velocity there is 0. So that u dot n is 0 all the time because the velocity u vector is always 0. So then let's try to evaluate the this mass flow rate here on this surface 1 and surface 2. But first of all, let's try to think about this case where the case 1, velocity is uniform on surface 1 and 2. As we know, we have a viscosity, so therefore velocity cannot be uniform unless the solid wall is moving at the same speed as the flow. Therefore, there's no relative shear. But again, this is a sort of the idealization. So if velocity is uniform on the surface 1 and 2, how do we evaluate this integral at the top right corner? So in this case, the surface mass flow rate or surface mass flux is u dot n and dA, cs in rho u dot n dA plus cs out rho u dot n dA. So you first need to identify on which control surface we are getting fluid particles, on which surface we're losing the particles, fluid particles. And how do we do this? So here the flow goes from left to right, so which I should have mentioned. So flow goes from left to right. So in this case, we have a uniform fluid going to the right. So this is my velocity vector, but I can probably suppress the velocity vector notation because this is a uniform flow. Okay. So then on the surface 1, you see that the fluid goes to right here, and whereas the outward normal vector is pointing to the left. So this might be clearer becomes if I define the streamwise direction as x. Then to do this integration, maybe I should assume that the density is constant, but the cs in, that's going to be the surface 1, and density, and this u dot n is minus u. So, and here the u without the arrow vector symbol is going to be the magnitude of the uniform velocity. So then cs out, on which I'm losing the fluid particles, that's going to be surface 2, and density, and on the surface 2 here, and you can see that the red arrows, which is indicating the fluid velocity, it's pointing the same direction as n2, which is the outward union normal vector of the surface 2. Then this term in the parentheses is going to be plus u times dA. So if we assume that the density is constant, and again this velocity u is constant, so I have this minus rho u on the surface 1 dA plus surface 2, and I should take this density and the velocity out, rho u dA, and minus rho u a1, area of the surface 1, plus rho u a2, and they should be 0 if the area 1 and area 2 are the same. If the areas are different, then the it's not going to be 0. But say if I can say this is the u1 and u2, it's a capital U1 and U2, then perhaps this expression should be minus U1, and it should be plus U2. Then I need to erase this 2 as well. So U1, U2, then again U1 and U2. So depending on how large A1, A2, and U1, U2 are, then you can have a different expression. So if the velocity is uniform, like I show you here, then velocity can come out of this integral, and we actually don't have to worry about anything. But things get a little bit more difficult if the velocity is not supposed to be uniform. Say on this the control surface. Say, let me redraw the control surface only. Say we have this control surface like this. And let's assume that our velocity profile is actually not uniform. Say this is kind of the parabolic. It's maximum at the center line. It's 0 at the solid wall. So let me calculate this quantity only on the surface 1 because the same idea applies on the surface 2. So this is my velocity, and this profile is given like u naught 1 minus lowercase r capital R square, and x direction is the streamline direction, R is the radial direction. So let's try to integrate this the parabolic velocity profile on the surface 1 only. So here is my surface mass flux, rho u dot n dA. How should I integrate this quantity? So again, let's follow the procedure. On the surface 1, so density. So here, u dot n is by the way, it's a vector notation, so I actually need the elementary unit vector along the x direction. That's I. So then my velocity u is going to be u dot 1 minus lowercase r over uppercase R square that times the elementary unit vector along the x direction. Then and of course the pipe radius is uppercase R. And that's gonna be my velocity u, velocity vector. So I have a magnitude and direction, which is I. So then this is dotted with the n1 vector. But this n1 vector, the unit outer unit normal vector on the surface 1, this is actually minus I because it's pointing negative x direction. So then I have this curly bracket and dA, and this is n1 hat. So now I can do a little bit of algebra. So density is assumed constant. U naught is the maximum velocity. That's also given as a constant. So I have a minus sign coming out of this integral. So this will be 1 minus lowercase r square dA. So I need to do this integration. So how do I do this? So again, here the integration variable is a, which is the area, but this is the integral over this infinitesimally small area. And we need to do the integration of the term within this square bracket, 1 minus lowercase r over uppercase R square. So meaning that to do this integration, we need to express this dA in terms of the R or vice versa. But here I'm going to choose to represent this dA in terms of this radial coordinate system. So if you look at this, the surface from the either minus x plus x direction, so cross-section area looks like this. It's just a circle. And we think about this infinitesimally small element, say something like this, as we did in the class, but this is not really great because this is cylindrical geometry. So one usually common method is to say, if you think about like a pizza slice, then this is one way to get this dA. this is a dA, can we express this dA in terms of r, and that is this going to be useful? So this is dA, so radius is r, and for this area, the corresponding the infinitesimally small angle is r times d theta. This seems to be useful, but there is a problem, because the integrand, which is 1 minus r over r squared, this is a quantity that's varying along the radial direction. In other words, fluid velocity is changing along the radial direction like this, but the parabolically. So it's maximum at the center line, and it's minimum at the minimum or zero at the radius, capital R. So meaning that on this infinitesimally small surface element, dA, if you draw it, if you choose to use this type of the infinitesimally small element, your velocity will change parabolically within this element. I mean, this term 1 minus r over r squared, this term varies within this dA. So then it's going to be a poor choice, because the reason why we choose this infinitesimally small element is that we want to think about very small area element on which the variation of the integrand is doesn't exist. So we want the variation of this integrand, this term, we want its variation to be not to exist, meaning that we want this integrand to be constant, uniform on this area. So this is going to be a poor choice. Let's not do this. Instead, we want to slice this area in the following way. So because the integrand is changing along the radial direction, but it doesn't change. Integrand doesn't have a dependence on the azimuthal direction or circumferential direction. So a better way to think about to having this infinitesimally small element is to have this kind of ring-shaped geometry. So this is useful because if you move, so say this is a dA. So then you have a radial location R, okay, and the maximum radius is capital R. And if you think about this geometry, then this integrand term, which is 1 minus r over r squared, it is only a function of the lowercase r. So therefore, the integrand is constant, remains constant on this infinitesimal small area element dA. Okay. So in this case, we have along the radial direction, this thickness is dr. So then how do I represent the dA in terms of the radial coordinate? So this is a ring, but what you can do is that you can actually cut here, and you can draw this geometry like this. Used to be a ring, but now I cut it here. Its height is dr, and its length is basically the length of this circumferential length of this circle. That's going to be simply 2 pi r. So therefore, this area of this ring geometry is 2 pi r dr. Okay. So then, in fact, you can actually get it really quickly if you can compare this with this well-known formula for the area of the circle, and you take a differential. It's like taking a derivative. It's going to be 2 pi r dr, which is equivalent, but the one that I talk about is more based on the geometry, whereas the one that I'm comparing with is based on this calculus. So now I get this expression for the area, dA, infinitesimally small area, but now it is written in terms of the radial direction variable. And now I can substitute this thing into here. So then let me evaluate this integral. This is going to be minus rho u naught on the surface 1 minus lowercase r, uppercase all square. And instead of dA, let me use the 2 pi r dr. This is I think there's some area factor. Then all you need to do is to integrate this one, this integral, rho u naught. Let's try to expand it. So, so 2 pi r minus 2 pi r cube r square and dr. Then we do the integration. And it's rho u naught. So I still have 2 pi factor, but let's keep it because it's too late. 1/2 r square minus 2 pi 1/4 r to the power of 4 r square. You do the integration from 0 to maximum radius r minus rho u naught. This is going to be 2 pi 1/2 r square minus 0 square minus 2 pi 1/4 capital R to the power of 4 r square minus 0 to the power of 4. I have a square bracket, so minus rho u naught. It's going to be pi r square. So this is going to be pi over 2 r square. Then finally, it will be minus 1/2 rho u naught pi r square. We want to combine all this constant. Minus pi over 2 rho u naught capital R square. Okay, so this is how you evaluate. So basically, you get this expression for this the infinitesimally small element dA, and you do the integration. Okay, this is everything I have today, and thanks for watching.